This is 24, 23. And it says you have a large horizontal sheet of charge. So I'll draw that kind of a large rectangular sheet like that. And it gives you the surface charge density, sigma. It tells you sigma equals 9 microcoulombs. Yes, 9.00 microcoulombs per meter squared. And it simply asks you, what is the electric field a small distance from above the middle of the sheet, right here. So what's the field, not here, but if we just go up a little bit, what's the field here? So it seems like a strange problem because they don't give you much information. They don't tell you the size of the sheet, they don't tell you how far away you are from the sheet, or anything. They want the electric field. So that is your hint that you have to make the approximation that the sheet is infinitely large. Okay? Let's think about this for a second. If we look at the sheet on its side, let's just look directly side on, so we only see it as an edge. And let's find the middle here. And let's say we're only going up to here. So we know that these are a bunch of little elements charged dq. Right? And we can think about symmetry, and we can think if you're right in the center, like it says, then you know this little piece and this little piece will create electric fields that cancel each other out in their horizontal components and only leave a vertical component. And of course this piece right in the middle will give you a big vertical component, and pieces farther away will give you smaller components. And in the end, we've done this before with symmetry, you'll only have a vertical component if the thing is in the center. Since it has edges, if you move away from the center, you'll have horizontal components. But one thing we know is we expect a field with a vertical component. We could think about using Gauss's law to figure this out, because this chapter is, after all, about Gauss's law. So we could think then that usually you draw a cylinder whenever you're faced with a plane. And for a finite sheet, this actually is a problem, because right in the center, this will indeed be an E field that's only pointing that way, and actually down here, it will be an E field only pointing down. But since it's a finite sheet, as you go away from the center, it does actually bend over a little bit. It'll bend a little bit like that and a little bit like that towards the edges. And the magnitude will change a little bit as you get different distances away from the surface. And this would make the problem hard. To do that vector calculus of that E dot dA would get tricky, even though the lateral component, the horizontal components may cancel. But you want to, and also to do that, you would have to know some distances, and you weren't given any. So since it says it was a large sheet of charge, and we're calculating the field fairly close, what we do is ignore these edge effects and just treat it as an infinite sheet of charge. Which actually we can do, because we're right on the center, and we can technically shrink our Gaussian volume as small as we want. We can make our Gaussian volume so small that the sheet really is essentially infinite. So in this case, the book, I don't think, was quite clear enough explaining that you should treat this as an infinite sheet of charge. You need to kind of learn when to do that. In a quiz or an exam, we would probably be a little bit more explicit about letting you know that you need to treat this as an infinite sheet of charge. The electric field above an infinite sheet of charge is E is sigma over 2 epsilon naught. So you can just memorize that, or look it up, or whatever you want to do. We can go ahead and derive it real quick. If we're treating this as an infinite sheet of charge, then we can just look at this case for Gauss's law, and rather than just writing the answer, we can say that the integral of E dot dA equals the total charge over epsilon naught. So the integral of E dot dA, well, we know that the E field will always point up, so we know the sides give us no contribution. We know it's really just the E field at this height, Z. So let's say this thing is a height of 2Z. So we're Z up and we're Z down from this axis. So this will be the Z direction. So the height Z and a depth, negative Z is where these two surfaces are. And let's say they have a radius R, like that. Okay. So there's no flux from the sides. There's only flux through the ends. And in both cases, the flux is positive because the area vectors are like that, and down here, and then the E fields are in the same direction. So it's really just 2 times the E field at Z, or the E field at that height z times the area, pi r squared. So that's the flux. It's just the flux at the top and the flux at the bottom. And then the total charge is what? It's pi r squared times the charge density. Looks like an r. Pi r squared times the charge density sigma, and then that's over an epsilon naught. And you can see what's going to happen. We're going to get the answer I quoted a minute ago. The pi r squareds canceled out, will cancel out, and you have that EZ, E at some height z above the plane, is going to be sigma over 2 epsilon naught. And that's interesting. That means that it's constant. The E field above an infinite plane of charge is constant everywhere. It can do that because it's an infinite plane of charge. It's a lot of charge. It creates a really large electric field. Here we have a finite plane of charge, but we're really close to it. So we really aren't sensitive to what's going on really far away. Anyway, it did ask for the value of the charge, of the field. So let's say E then, at any height z for an infinite plane or near the surface for a finite plane is, what is it? It's sigma. So it's 9 times 10 to the minus 6 coulombs per meter squared over 2 times 8.85 times 10 to the minus 12. I always have to look it up. Coulomb squared per Newton meter squared. And if you run those numbers, you get 5.08 times 10 to the 5 newtons per coulomb is the E field magnitude. We were asked for the full E field, so we should give the direction. And I said it's going to be pointing in the plus z direction, so we can just put a k hat on it. K hat being the unit vector in the z direction.